If we run this experiment many times with different 1 probabilities, we obtain a map of how the time evolution of mean glider density varies as a function of p. Here, brighter colors correspond to higher densities. This map has several interesting features. First, we see a sharply delineated range of 1 probabilities over which gliders arise. Second, we see a well-defined epoch of time over which gliders typically exist. Finally, we see 2 narrow bands of long-term glider persistence. Note that glider density has been multiplied by a factor of 5 on the right side of this plot to help bring out these faint bands more clearly. From now on, we'll focus on the structure of vertical slices through this density plot, which correspond to the mean glider density as a function of p at fixed times. Our goal is to try to characterize the processes underlying the changing structure of these slices. To do so, we need to develop a kind of statistical mechanics of gliders. We start with G0, the density of gliders in the initial random state. This can be computed exactly. After 1 step, this initial glider density is transformed to another density, G1. This transformation from G0 to G1 is driven by 2 processes that change glider density: the creation of new gliders and the destruction of existing gliders. Equivalently, we can describe it in terms of the persistence of existing gliders and the creation of new gliders. Each of these processes can be formalized as a time-dependent operator acting on glider density. Together, this decomposition accounts for the change of glider density from time 0 to time 1. Note that the initial randomly generated gliders are almost completely destroyed in the first step, with only a small fraction persisting. In fact, almost all glider density observed at time 1 arises from the creation of new gliders, which occurs at 2 different values of 1 probability. Calculating these glider density operators is essentially an exercise in combinatorics. The details of these calculations are in the paper, but they basically require counting the sizes of various subsets of configurations involved in the creation, persistence, or destruction of gliders. This diagram illustrates the setup for the calculation of the 1-step glider density operators shown in the previous slide. Armed with these glider density operators, we're now ready to explain the time evolution of glider density in terms of the processes of creation, persistence, and destruction that underlie it. We've already examined the transition from time equals 0 to time equals 1, in which 2 peaks of glider density arise. Significant destruction of existing gliders and creation of new ones continues for another step. But then, over the next several time steps, destruction decreases and creation begins to dominate, alternately raising first the left peak and then the right peak. By time 5, we have a fairly symmetrical situation in which 2 peaks, supported by significant glider persistence, are separated by a valley. This valley floor then rises until by time 60, we have a wide mesa of maximal glider density. This rise is driven by a small dominance of creation over destruction at the center of the valley. Note that the creation-destruction imbalance slowly decreases over time, temporarily canceling at time 60. Beyond time 60, the mesa begins an extremely slow fall, with destruction now very slightly dominating creation. As the mesa falls, the peaks of glider density at each end begin to reemerge until the valley floor collapses. Creation and destruction cease, and only the peaks of glider persistence remain. Thus, we see how the patterns of glider density evolution observed in our initial experiment arise from a complicated density and time-dependent interplay between creation, persistence, and destruction processes. The paper also describes a few extensions and refinements of this analysis. For example, it turns out that the narrow bands of glider persistence that we observe are closely related to transitions in the asymptotic density of the game of life universe as a whole. This suggests that, rather than treating questions about the origin, proliferation, and extinction of gliders in isolation, we should study them within the broader context of the general statistical mechanics of the game of life. We can also further refine our calculations of the glider density operators. For example, glider creation can be decomposed into the separate contributions made by each of the two different forms that a glider can take. Interestingly, we find that one form dominates glider creation at lower initial 1 probability values, while the other form dominates at higher values. As a second example, glider persistence can be decomposed in terms of the 6 different classes of non-destructive perturbation that were identified in previous work. We've now reached the point where you would normally get to ask me questions, and you're certainly free to do so. Unfortunately, since I'm only a recording, I won't be able to provide you with any answers right now. However, if you're willing to email your questions to my original, I'm sure he would be more than happy to answer them as soon as he can. Thank you.
So yes, as Randy says, please email your questions to him and take a look at the paper. And so I suppose we'll move straight on to the next lightning speaker, which is Emily Dawson.
Okay, hi everyone. So I want to talk to you about a solution to this problem that I'm sure a lot of us have, which is that we want to make hypotheses and inferences about low-level evolutionary dynamics. So for instance, we might want to hypothesize that a given condition in our experiment works differently than a different condition because lineages in that population are maybe more able to cross values, or they get caught on a certain type of fitness peak. And that's all well and good. Those are fundamentally hypotheses about this, the way that a lineage, so a sequence of individuals from an ancestor all the way to an extant organism, are traversing a fitness landscape. And this is a figure from our companion paper where we visualize that, and we show that you can get a lot of useful information by visualizing it. The problem is that visualizations like this don't scale well. In most of our experiments, we have thousands of lineages, and we can't look at all of them on a visualization like this. So ideally, it would be great if we could have some sort of summary statistics that capture all of those low-level processes that all have a great deal of stochasticity when they occur, and can tell us something about the outcome of them in aggregate. So we proposed a few ideas for how to do that. And so all of this fundamentally derives from the idea that we can represent a lineage as a sequence of states. So generally in evolution, we start with some ancestor organism like this, and it reproduces, makes a copy of itself. That offspring reproduces, perhaps it has a mutation, and so on and so forth until we end up with the individual that we had at the end of our experiment. And so then we have this sequence, a lineage of all of the individuals that led to it. So this is great. This is already easier to deal with than that kind of zigzaggy figure we had on the last slide. But still, this is a lot of information. So much information that in many cases it is very unwieldy to work with, and it is not the most useful level of abstraction. So we can summarize this into a sequence of unique genotypes instead of all the individuals. But even this may be unwieldy. And so in some cases we may want to summarize it further into phenotypes, or even aspects of phenotypes. And so with this idea, we can choose whatever resolution we need to answer our question and balance that with the amount of data we have to work with. Okay, so once we have this, how can we actually analyze it and make use of it? We came up with a few classes of analyses that it may be useful to do on these sequences. So the simplest one is the length. We can just count how long the sequence is. And like all of these, the interpretation of this is going to depend on your system and the way you set up your experiment and what this is a sequence of. But in general, length might get at things like the number of generations that occurred, which could potentially tell us about life history strategies, or it may be something different. Relatedly, but differently, we can look at the number of unique states in our sequence. So this will get at how much is it exploring the space of potential states? So that could be the fitness landscape or the range of phenotypes. A similar but importantly different metric is volatility. So how many changes of state occurred. For the most part, this will correlate very closely with the number of unique states, but when it doesn't, that's telling us something really important. That's saying there is some sort of cycling or oscillating between fixed states. And so, again, depending on your experiment, that's often useful information to be able to extract from these sequences. Additionally, we can record metadata about these state changes. So we can record what type of mutation took us from one state to the next state. And then we can go back along the lineage and sum that up. And so this is useful if we're, for instance, comparing the number of insertion or deletion mutations that occurred along the lineage of the fittest organism to that metric for the average lineage in the population. And if we see that, oh, there are way fewer indels for the fittest, that might indicate that they are not, in general, advantageous mutations, or vice versa. Similarly, we could record different metadata, like the fitness of these individuals, and we could count the number of deleterious mutations that occurred. And so that will get at common hypotheses that we have about things like valley crossing. Okay, so that's an individual lineage. Usually we have a phylogeny instead of just one lineage, you know, a whole tree of how different lineages connect to each other. And that provides us additional information, which biologists have already done a lot of excellent work with. So if you're interested in this, I highly recommend this review by Tucker et al., where they summarize the different ways that you can measure a phylogeny. And so in general, this can get at things like the total amount of evolutionary history that your phylogeny represents, with the richness. It can look at how far apart different phylogenetic clusters are from each other with divergence. And the regularity will tell you about the actual underlying topology of the phylogeny. And so these are really, I think, underused in ALIFE because unlike biology, we have perfect phylogenetic information. We could do a lot of really useful analyses with this. Okay, so we presented a bunch of metrics. It's not very useful to have them for interpretation if we don't have an intuition for how they'll behave under different circumstances. So I don't have time to go into all of this, but if you're interested, there's a lot of data in the paper where we basically had these 4 example landscapes that we took from a competition on niching, just to have landscapes to work with. And we evolved some very simple populations on them with tournament selection, and we looked at how these metrics responded. So just here's an example where we were looking at various metrics as we changed selection strength. And you can see in this simple example, most of them aren't very problem dependent. There's one example here that is. The volatility in this case was more gentle for that one problem. And just to give you a flavor of how we analyze this, we use that visualization I mentioned earlier to look at what's actually happening to the lineage in these circumstances. So here we can see that it's basically a property of how smooth the valley between these 2 fitness peaks are. It's determined by how far up the fitness peak a mutation needs to carry an individual in order for it to survive. Okay, so basically the takeaway message is that if you are also having this problem of way too much data to be able to analyze your underlying hypotheses, we suggest you try out these metrics. We have a C++ implementation at that middle link there. It's header only. If you're using C++, the idea is it should be very easy to plug into your existing software without having to write a bunch of new code. And if you're having trouble with that, please talk to us because we want to help. Thanks.
Okay, we have time for a few questions. Are there any questions? Yeah, Matt.
So you mentioned some of the tools that biologists use to look at phylogenetic trees, and I'm just curious if you're familiar, if there's been work that's been done in taking artificial evolution, where, as you said, we have all of the data of an entire history, and to sort of validate tools like BEAST, if you're familiar with it, that takes existing genetic data and tries to reverse engineer what the phylogenetic tree in natural history was. Do you know if there's any work along
That's a great question. I'm not familiar with these specifically, but I know there's been a lot of work on testing general phylogenetic reconstruction methods. I think, Charles, did you do some of that a while ago?
We have actually multiple papers looking at that exact sort of concept and examining what information is being used and ignored based off knowing what the real phylogeny looks like and then what the reconstructions are and what sort of errors are. Cool.
Thanks.
yeah, there's another question from Hiroki.
Thanks, Emily. I'm sure you explored lots of different ways of quantifying stuff by implementing and examining. So I wonder if you have come up with a new way of measuring stuff that hasn't been used in real biological studies that you want to propose to them.
That's a great question. We looked a lot in the biological literature. I cannot claim that we looked at all of it. There's a lot. But some of these lineage metrics that I was talking about in the first half before I got to the phylogeny stuff, I'm not aware of them all having been used in biology before, because it's often harder to do this kind of abstraction on biological lineages because we don't have perfect lineages as often. They're often inferred. And also, I mean, things like looking at the length of the sequence isn't something that would make as much sense in biology in a lot of cases. So I think those are potentially new.
One more question? So I have a question. So how do you think these measures would change if you were to use high-dimensional landscapes rather than low-dimensional ones?
That is a fantastic question. So the thing we were originally trying to do when we came up with these is make inferences about high-dimensional landscapes that we couldn't visualize. And so I think it's one of the fundamental problems in dealing with fitness landscapes is that we probably have bad intuition about high-dimensional fitness landscapes. I have a plan to try and visualize a one level higher fitness landscape and watch how lineage goes through it to try and get at what the disconnects are there. In the companion paper, but I think it's hard to be sure. So we wanted to develop our intuition on these simple landscapes first. We'll try and scale it up to higher landscapes. So we were playing with data from evolving Othello players, which is obviously very high dimensional. And the issue there, I think, is just establishing ground truth for whether what we think is telling us about Othello is actually what's happening. And I think that's a problem we're still working on.
Okay, thank you very much. And so the next item of talk is from Dave Ackley.
Thanks for staying, everybody. This is the title of the paper. I kind of made it a deliberately boring title because I think it's actually really badass work. And I didn't want to have to gild the lily. But I'm not going to really talk about it. I'm going to spend the time giving the context behind the work. And then hopefully you'll be propelled to want to read about it when we get to it. So I've been working on this area for quite a number of years, and it's because I have this belief that computation, manufactured computers, the way that we do it today is deeply broken. And it's broken in the following sense. The whole idea of hardware determinism, that a computer guarantees, the hardware guarantees, same program, same input, you're going to get the same output. If you do it again, you get the same output. That idea is training wheels for computation. And we've been keeping the training wheels on our computer architectures for 70 years. As Inman was saying, real living systems, they don't do that. Living systems expect to deal with errors and uncertainties all the way up the computational stack. We don't. We think hardware is going to take care of it. And therefore, software acts like this incredible prima donna where everything has to be perfect. Wait. 6. You're welcome. This is software. And if anything goes wrong, software throws a tantrum and says, I'm in my trailer. We have to get beyond that. The flip side of it is that doing it the way we do it, we focus on efficiency. All we care about is correctness and efficiency only. CEO. Correctness and efficiency only. That's considered all you need for software. But in fact, what you need is robustness and working pretty well. We can have that, but we will not have that because we're stuck in the correct and efficient only attractor. So I suggest the future of computation is this idea of indefinite scalability. We won't have a CPU, we won't have a central processor. We will have oceans of little teeny processors that are interacting, they're failing, we're adding more to the thing, we're building the machine while it's running. And software, the entire computational process, will not guarantee you get the right answer. That was a crap guarantee anyway, as Inman also pointed out. Instead, we will have best effort. I will do my damnedest to get you an answer that's pretty good. And that's all you could ever really guarantee anyway. So, this is my mission. Fix computing. Make the world a better place. We have these, 100 million bank account, credit card accounts get lost, 350 million information gets leaked. We think that's normal. It's crazy. We are living in crazy land. So, I want to tell you what I've been doing for the last decade. I started in this thing with hardware. These are little computer tiles that were marketed briefly under the name Illuminato Ex Machina, and you get the idea. I did not pick the name, that was a marketing name. These individual little tiles that plug together, they share power, they share communications, you update the software in one of them, and it goes hop to hop to hop to hop until the whole thing is updated. I wrote the operating system for this, that was great fun. They had their limitations. They were sort of a 2000 era cell phone CPU power. I went and looked to the software side of things. What are we going to put inside these little tiles? And the answer was going to be something like a cellular automata, but not the traditional one. Number one, it cannot be synchronous, because we're adding new tiles all the time. They run different speeds. We cannot wait for the last tile in Pluto to finish the tick before we go on to the next one. We cannot assume determinism. So the game of life is plain gone. We have to figure out how to compute without that. So these are the things, these are examples of a little sort of, these atoms would connect up and make little chains, and there was a copier so you could actually reproduce the chains, and it was very organic in the sense that it didn't even wait for one copy to be complete before it would start copying the copy that's copying in progress. Why? Because there was room, there was space, you could get another guy in there, it would just happen. At the same time, so that was hardware, that was software, and then there was advocacy, because I realized that this correctness and efficiency only idea is so deep in our brains, especially in computer science, that we don't even realize it's determining us. I can't take time on this, but this is a sorting algorithm. Imagine sorting where the comparisons might be wrong. Just too bad. Now our beautiful quicksort, merge sort, the pinnacle of computer science sorting theory, they do terrible. Why? Because they're designed to exploit the hardware determinism. Whereas bubble sort, pitiful, horrible, black sheep, everybody hates it, bubble sort is great. Why? Because it doesn't up the leverage. It compares things redundantly, it only moves them little bits, so if it gets it wrong, it doesn't move them very far. The bottom line here is that efficiency and robustness are at odds over redundancy. Robustness requires redundancy. Efficiency eliminates redundancy. So you've got to be careful when you motivate your work, especially if you're an ALIFE, on the grounds of efficiency. That's a red flag. We all do it. But realize you're vulnerable, because you just said, I just made my system fragile right there, wherever it was that you're claiming efficiency is the result. So we went on, we invented programming languages to help us express transitions in this asynchronous, non-deterministic cellular automata language. Here's an example, a fork bomb. You put one in the middle, you let it run, it grows, it goes crazy. Okay, well, big deal. Once you start having a little more complex transition functions, the code isn't quite as simple. So the work that's actually new, the work that you can read in the paper this time, is a language called SPLAT, which stands for Spatial Programming Language ASCII Text. And the idea is you write little patterns with characters, Emacs picture mode, saying that sign is me, the dot is anything. If you match that pattern, you can replace it with a me and another copy of me. There is a fork bomb element. And you can very quickly get to more complex ones. These are rules that allow us to make a pairwise, a two-layer thick line grow in and out on the basis of the density that's inside. And we use it for making a simple cell membrane. And it looks something like this. A seed, it sprouts the two shades of blue, or the inner membrane, the outer membrane, and it just goes like this. And the idea is the membrane has no state. It just says, go away from high density, go toward low density. And as a result, when the insides move, the membrane moves with it. So, is this real? Is this a simulation? We're now taking the simulator, putting it into physical hardware tiles, and letting them talk to each other. Is it real? Is it a simulation? Of course, it's both, depending on how you look at it. I've used up more of my time. Thank you so much.
That's a very inspiring talk. We have questions. There's one from the back.
Thank you very much. I thought that was a really fantastic talk.
Thank you.
How are you going to convince people that deterministic hardware and software can be, if you want, improved with this new approach? I mean, people like to blame things. They like to blame other people. They like to take something and just make it responsible for mistakes, for errors, for...
It's been great for the software people. Anything that goes wrong, they say, it's a hardware problem. My hands are clean. And we have to renegotiate that boundary, and that's what best effort is all about. Hardware promises its best effort, but it reserves the right to fail and fail arbitrarily. So software has to carry some of the load. Are people going to like that? No. Tough. So exactly how we get to it, I don't know. My goal is to get as many people as I can, as excited I can about wanting to work on this, about thinking that there's an alternative to what we're doing now, and see if we can't get to a tipping point.
Next question is from Robin.
Brilliant, as always. I think maybe my question is going to be reminiscent of questions I've asked you before at talks that you've given that are similar to this one.
They're all the same.
But going back to Inman's point, one of Inman's points, I think is that even though software appears to be to adhere to the CEO paradigm, in point of fact, it doesn't.
It depends on the software. Because
it's failing all the time, and we're living with software failures all the time, and we do get on the plane anyway. And there's various versions of software failing and dealing with failures that are out there in the world right now that aren't a result of engineering a new software the right way, the way you're doing it, but rather, we have internet protocols that are waiting around for packets to come, and so I'm wondering if there's an ongoing software engineering evolution that's kind of creating a path towards what you're talking about without doing things the right way from the ground up.
Norm, that's great, There is, and someone was talking about it in the Signal GP talk the other day, the whole idea of going to event-driven. If you make the chain between input and output be as short as you possibly can, and then lean back on the state of the environment, then you have less at risk. You can still, obviously, you can use event-driven stuff to do towers. I know I make an incredibly hard-welded system, but by and large, you get less dependencies with shorter program chains. So that's an example of how it's happening anyway. My concern is that it's happening so slowly, and the urge to domination, the urge to compute as a dictator with top-down, must go like this, must go like this, is hard to resist unless we understand the costs. So I'm trying to plant a flag all the way at the other end and say, look, it could be this. We could actually compute this way. It's not too advanced, but it's unbelievably tough.
I think we're going to take one last quick question from Tom Fraser.
I think your proposal matches very well quantum computing, right? I mean,
Quantum
computing. IBM recently came to a university and they were all about, oh, we need to bring down the error rates and that. Maybe the proposal is to say you don't need to do that. Actually, just take advantage of it and just implement computing differently. Maybe ALIFE could actually make a big contribution to developing the architectures of quantum computing.
Yeah, that could be. At this point, I have to confess that I'm a quantum curmudgeon. And I actually believe that once error containment and decoherence are properly accounted for, all we're going to get out of quantum is huge constant factors. We're going to use it because huge constant factors are nice, but it's actually not going to be magical. And so it's orthogonal to this issue, that it would be nice if instead of using our quantum computers to do a NAND gate or to play tic-tac-toe, we thought about doing something more like this, but it's a separate issue.
So there are plenty of other questions. Unfortunately, we have to end it here. There's going to be an announcement. But if those who want to ask questions are around at the very, very last session of the day, as a workshop, then Dave will be there too. So that would be one place where this discussion will be picked up. Otherwise, we'll stay in the coffee.
Quick announcements. Well, time flies. Thank you so much for sticking with us so long. We had so much fun, and it's not over. So I remind you that after coffee, not only do we have one more session, but also we'll have the LC Special Earth Life ALIFE workshop starting. That's very exciting.